express very general computation as a sort of something that looks like message passing. You have nodes, and they all store vectors. And these nodes get to basically look at each other, and it's each other's vectors, and they get to communicate. And basically, nodes get to broadcast, hey, I'm looking for certain things. And then other nodes get to broadcast, hey, these are the things I have. Those are the keys and the values.
So it's not just attention.
Yeah, exactly. Transformer is much more than just the attention component. It's got many pieces architectural that went into it. The residual connections, the way it's arranged. There's a multi-layer perceptron in there, the way it's stacked, and so on. But basically, there's a message passing scheme where nodes get to look at each other, decide what's interesting, and then update each other. And so I think when you get to the details of it, I think it's a very expressive function. So it can express lots of different types of algorithms in forward pass. Not only that, but the way it's designed, with the residual connections, layer normalizations, the softmax attention, and everything, it's also optimizable. This is a really big deal because there's lots of computers that are powerful that you can't optimize, or that are not easy to optimize using the techniques that we have, which is backpropagation and gradient descent. These are first-order methods, very simple optimizers, really. And so you also need it to be optimizable. And then lastly, you want it to run efficiently on our hardware. Our hardware is a massive throughput machine, like GPUs. They prefer lots of parallelism. So you don't want to do lots of sequential operations. You want to do a lot of operations serially. And the transformer is designed with that in mind as well. And so it's designed for our hardware, and it's designed to both be very expressive in the forward pass, but also very optimizable in the backward pass.
And you said that the residual connections support a kind of ability to learn short algorithms fast and first, and then gradually extend them longer during training.
Yeah.
What's the idea of learning short algorithms?
Right. Think of it as so basically a transformer is a series of blocks, right? And these blocks have attention and a little multi-layer perceptron. And so you go off into a block and you come back to this residual pathway, and then you go off and you come back, and then you have a number of layers arranged sequentially. And so the way to look at it, I think, is because of the residual pathway, in the backward pass, the gradients sort of flow along it uninterrupted because addition distributes the gradient equally to all of its branches. So the gradient from the supervision at the top just floats directly to the first layer. And all the residual connections are arranged so that in the beginning, during initialization, they contribute nothing to the residual pathway. Mm-hmm. So what it kind of looks like is, imagine the transformer is kind of like a Python function, like a def. And you get to do various kinds of like lines of code. Say you have 100 layers deep transformer. Typically, they would be much shorter, say 20. So you have 20 lines of code, and you can do something in them. And so think of, during the optimization, basically what it looks like is first you optimize the first line of code, and then the second line of code can kick in, and the third line of code can kick in. And I kind of feel like because of the residual pathway and the dynamics of the optimization, you can sort of learn a very short algorithm that gets the approximate answer, but then the other layers can sort of kick in and start to create a contribution. And at the end of it, you're optimizing over an algorithm that is 20 lines of code. Except these lines of code are very complex because it's an entire block of a transformer. You can do a lot in there. What's really interesting is that this transformer architecture actually has been remarkably resilient. Basically, the transformer that came out in 2016 is the transformer you would use today, except you reshuffle some of the layer norms. The layer normalizations have been reshuffled to a pre-norm formulation. And so it's been remarkably stable, but there's a lot of bells and whistles that people have attached on it and try to improve it. I do think that basically it's a big step in simultaneously optimizing for lots of properties of a desirable neural network architecture. And I think people have been trying to change it, but it's proven remarkably resilient. But I do think that there should be even better architectures potentially.
But it's you admire the resilience here.
Yeah.
There's something profound about this architecture that leads to resilience. So
yeah.
Maybe everything could be turned into a problem that transformers can solve.
Currently, it definitely looks like the transformer is taking over AI, and you can feed basically arbitrary problems into it, and it's a general differentiable computer, and it's extremely powerful. And this convergence in AI has been really interesting to watch for me personally.
Interesting.
What else do you think could be discovered here about transformers? Like, what surprising thing? Or is it a stable, we're in a stable place? Is there something interesting we might discover about transformers? Like aha moments? Maybe it has to do with memory, maybe knowledge representation, that kind of stuff.
Mm-hmm. Definitely the zeitgeist today is just pushing, like basically right now the zeitgeist is do not touch the transformer, touch everything else.
Yes.
So people are scaling up the data sets, making them much, much bigger. They're working on the evaluation, making the evaluation much, much bigger. And they're basically keeping the architecture unchanged. And that's how that's the last 5 years of progress in AI, kind of.
Oh, right. hearing from Andre Karpathy and Lex Friedman talking about AI. Lex Friedman's podcast was called the AI Podcast before it got changed. Amazon quarter was decent, I thought. Let's see AWS, the all-important division. I think it stands for Amazon. I don't know. I just don't. I did not have the right number in for Q3. That's weird. It's like Oz. Like Jaws without the J. Oz. Well, whatever this Oz business is, didn't look so good. 21,378 is pretty light. Only 20% growth. Yee! Aye! Oz. Amazon Wholesale Systems, I believe. Amazon Warehouse. Amazon Warehousing Sisters. Amazon Worthwhile Substances. The RDS fees. That's where Amazon makes all their goddamn money. All right, last quarter, AWS was 2538. That was also light. AWS growth has slowed to a crawl. 20% is still a lot of growth for most people. But Amazon had been growing like 40% or whatever for a while. So I guess for them, there's some years where it only grew 29. Let's see, 2020 was growing only 28, 29%. Then they had this big bump, maybe due to COVID. And then maybe we're getting back down to normal. They are saying, if you look at guidance for next quarter, though, they're going to have to make it somehow. And my guidance, my model sort of adds up to their guidance, which includes a 30% growth. So I don't know. I don't have a PhD now. All right, let's see here. We got North American net sales. That was from last quarter. Let's go back to this quarter. Okay, North America 93,363. It's amazing that they break even on on the whole Amazon website. Somebody told me that I could have $128 billion of revenue in one quarter, but I couldn't make a penny. Could you imagine that? Give me $128 billion of revenue, but no profits. No profits. Obviously, they have some special costs that we can't see. If we could see the actual Amazon operating business, I think we'd probably see profits. College. What was your major in college? College? What do you think this is? I grew up on the streets.